Voyager 1. The strange world beyond the Sun. There is a region of space so distant that the Sun no longer dominates the sky the way it does from Earth. Somewhere out there, Voyager 1 is continuing its journey through interstellar space, carrying instruments that have been operating for almost half a century. When scientists imagined what Voyager would discover beyond the Sun's protective region, they expected an extremely thin and relatively quiet environment. Instead, the spacecraft encountered something much more complicated. It detected changes in plasma density, energetic particles, magnetic disturbances, and a persistent pattern of waves moving through the material between the stars. The discovery changed the way scientists think about the boundary of our solar system. The Sun constantly releases a stream of electrically charged particles called the solar wind. This wind expands outward and creates a huge region known as the heliosphere. Earth, Mars, Jupiter, Saturn, and the other planets all exist inside this enormous bubble. For decades, researchers expected the outer edge of the heliosphere to behave like a fairly simple boundary. The solar wind would gradually weaken, particles from interstellar space would become more dominant, and a spacecraft crossing the boundary would enter a completely different environment. Voyager 1 reached this region in 2012. Its instruments recorded a dramatic reduction in particles originating from the Sun and an increase in cosmic rays arriving from the galaxy. These measurements showed that Voyager had crossed the heliopause, the outer boundary of the Sun's heliosphere. But the spacecraft did not enter a perfectly calm region. Instead, it found disturbances, pressure variations, energetic particles, and magnetic interactions that were far more complicated than many models had predicted. The boundary was not simply a wall separating the solar system from the rest of the galaxy. It was an active region where two different environments interact. Years later, Voyager's plasma wave instrument detected a very faint signal surrounding the spacecraft. The signal was weak, but it continued appearing as Voyager traveled farther away from the Sun. This was important because the signal gave scientists a way to study the density of plasma around the spacecraft. Previously, researchers often depended on temporary disturbances produced by powerful solar events to obtain information about interstellar plasma. Those events provided only occasional snapshots. Voyager was doing something different. It was traveling through the region continuously and recording changes along its path. The measurements suggested that interstellar space is not simply an empty vacuum. It contains variations in density, waves, magnetic fields, and energetic particles. In a sense, the space between stars has its own form of changing conditions. Of course, this is not weather like we experience on Earth. There are no clouds or storms in the ordinary sense. Instead, scientists are observing changes in pressure, particle density, magnetic activity, and energy. The exact origin of Voyager's persistent plasma signal is still not completely understood. It may be connected to natural oscillations within the plasma, or it could involve processes that existing models do not fully explain. Voyager discovered the pattern, but understanding exactly what causes it may require measurements that the aging spacecraft may not have enough power to continue collecting. The magnetic environment around the heliopause is equally fascinating. Scientists once expected the Sun's magnetic field and the galactic magnetic field to remain relatively separated. Voyager's observations suggested a much more complicated interaction. Magnetic field lines can rearrange themselves through a process known as magnetic reconnection. This can transfer energy and connect regions that might otherwise appear separate. That means the solar system is not completely isolated from its galactic surroundings. The boundary around the Sun is more dynamic than it first appeared. Voyager also detected highly energetic particles near the heliopause. These observations showed that the region can be much more active than the simple picture of a quiet border between two environments. This matters because the heliosphere provides Earth with a degree of protection from high-energy cosmic radiation. Voyager has not shown that this protection is suddenly disappearing. Instead, it has demonstrated that scientists still have much to learn about the forces controlling the size and behavior of the heliosphere. The Sun is moving through the galaxy, and the interstellar environment around it is not perfectly constant. Changes in external pressure and density could influence the shape and size of the heliosphere over enormous periods of time. So Voyager's discoveries are not only about a spacecraft billions of miles from Earth. They also help scientists understand the invisible environment surrounding our own planet. Then Voyager faced another problem. In late 2023, the spacecraft stopped sending usable scientific information. NASA could still detect a signal from Voyager, which meant the spacecraft was functioning, but the information being received was no longer meaningful. After extensive investigation, engineers traced the problem to a damaged portion of Voyager 1 and the final frontier, but Voyager 1's story does not end with the moment it crossed the heliopause. In many ways, that crossing was only the beginning of a much larger scientific journey. Far beyond the planets, Voyager is moving through an environment that cannot be seen with ordinary cameras. There are no landscapes, no visible clouds, and no obvious landmarks. Almost everything the spacecraft discovers must be understood through changes in particles, magnetic fields, and electrical signals. That makes every measurement extremely valuable. Voyager is effectively sampling the space between stars one small measurement at a time. One of the most interesting discoveries is that interstellar space is not completely featureless. The spacecraft has detected variations that indicate the material between stars is constantly changing. The plasma surrounding Voyager can become slightly denser or thinner. Energetic particles can increase or decrease. Magnetic conditions can change as the spacecraft moves through different regions. These differences reveal something important about our galaxy. Even what appears to be empty space has structure. The region beyond the heliopause also helps scientists investigate how the Sun interacts with its galactic surroundings. The Sun is not sitting still in the galaxy. It is moving through an enormous interstellar environment filled with particles and magnetic fields. As the Sun travels through different regions, the heliosphere may respond to those changing conditions. The size and shape of the solar bubble can therefore change over very long periods. That means the environment surrounding Earth is connected to something much larger than the solar system itself. Voyager provides one of the few direct opportunities to study that connection. Its journey has also changed the meaning of the word boundary. Before Voyager reached the outer edge of the heliosphere, it was tempting to imagine the solar system as a clearly defined bubble with a simple outer wall. But nature did not provide such a clean separation. Instead, the boundary contains interactions between solar particles and material originating beyond the Sun's influence. There are transitions, disturbances, and regions where magnetic fields interact. The farther Voyager travels, the more complicated the picture becomes. And that creates another mystery. If the environment outside the heliosphere is changing, what happens to the heliosphere itself over millions of years? Could it become larger? Could it shrink? Could its shape change significantly as the Sun enters different regions of the galaxy? Voyager cannot answer all of these questions by itself. But its measurements provide pieces of the puzzle that scientists can combine with observations from other missions and telescopes. The spacecraft's greatest contribution may therefore not be a single spectacular discovery. It may be the long-term record it has created. Voyager has been operating for an extraordinary amount of time. Its measurements allow researchers to compare conditions across enormous distances and across many years. That is something a short-lived mission could never provide. But continuing this investigation is becoming increasingly difficult. Voyager's power supply is slowly weakening. Every year, the spacecraft has less electrical energy available. That forces mission engineers to make difficult choices. Which instruments should continue? Which systems can be switched off? How much power should be reserved for communication? And how long can the spacecraft continue transmitting useful scientific information? These decisions are not made casually. Turning off an instrument can preserve energy, but it also means losing a scientific capability that can never be restored. Voyager's hardware was built during an era when computers and electronics were dramatically different from today's technology. The spacecraft contains systems designed nearly half a century ago. Yet those systems are still communicating across billions of miles. The engineering achievement is remarkable. But aging hardware brings another challenge. A component can fail without warning. A memory location can become corrupted. A sensor can stop functioning. A communication system can become weaker. And because Voyager is so far away, engineers cannot simply send someone to repair it. Every solution must be created remotely. This is where Voyager's mission becomes almost as much an engineering experiment as a scientific one. The engineers working with Voyager must constantly think about what the spacecraft can still do and what it can no longer safely attempt. A command sent from Earth is not immediate. There is a significant communication delay. That means the spacecraft must often operate without real-time supervision. Its onboard systems have to protect themselves when something unexpected happens. Engineers on Earth then wait for the spacecraft to report what occurred. This makes even a small technical problem potentially complicated. Yet Voyager has survived problems that seemed capable of ending its mission. Its continued operation is partly due to careful engineering and partly due to decades of accumulated knowledge about the spacecraft. Each time engineers discover a new way to preserve power or recover